Hello everyone and welcome to this week's webinar of Seds Online. We're really pleased to be able to offer all of these resources for free thanks to generous funding from the International Association of Sedimentologists, the IAS. This week we're really pleased to be able to host Peter Burgess, Professor Peter Burgess from the University of Liverpool. Peter began his professional career with 2 postdoc positions in Caltech and Liverpool respectively, before going on to become a lecturer in sedimentology and basin analysis at Cardiff University. In 2002, Peter moved to Shell to work as a regional geologist and carbonate specialist, and then in 2010 took up a position at Royal Holloway University of London as a professor. In 2010, Peter became Professor of Sedimentary Geology at Royal Holloway, including 2 years as head of department. In 2017, Peter moved to the University of Liverpool to be head of Earth Sciences, where he is presently a professor of sedimentary geology. And today we're going to find out if he's a big fan of signals. So without further ado, I'll hand over to you, Peter.
I think probably quite a few of the people here already know the answer to that, I'm suspecting. Yeah, so I'm going to talk about this work that actually we first presented, I think, last year at the SEPMA APG conference in wherever that was, back when we were allowed outside. This is work then that I did with Isabella Massiero, who helped write the Lobyte code, and Stefan Toby and Rob Duller, who Stefan was a PhD student in Liverpool's now a postdoc, and I think I saw him on the list of people in this webinar, and Rob Duller. And so basically Stefan and Rob, their contribution to this was lots of arguments about what it all meant, which is always very useful. So what I'm going to talk about, if I can get this to work now, is how do we distinguish an allogenic signal from autogenic noise in strata? This is a critical aspect of how we interpret and understand most stratigraphic sequences. And there's a nice example here on the bottom of the screen, which is a very old school photo montage done with printed photographs, none of this drone malarkey. This was back in the day when it was much more primitive. And this is showing some mid-Jurassic turbidite strata from the Naukem Basin. I can scroll through it and you can just catch a glimpse of my colleague Duncan McIlroy, who did fieldwork out there with me at the time. And the thing that's striking about this example is it's deep water turbidites, but arranged into packages, and you can see there are basically packages of sand separated by much more shell prone strata, and I'm not sure that I can go backwards, but oh yeah, there we go. And you can see that they occur on a few different scales, but basically those are probably, I think, lobe deposits. Typical interpretation of those in the literature, I think it would be fair to say, has been that they're low stand fan deposits, you know, sand prone intervals produced during low stands of relative sea level. But as ever, we can ask ourselves, is this simply seductive interpretation correct? And the reason we might wonder whether it is because often outcrop interpretations can be more modeling than observation, right? Now I'm an arch modeler, so I think maybe this is a contentious statement to make, but I think an awful lot of what is presented as outcrop observation is has got much more model content in it than perhaps we would initially care to admit. So that's a key question we need to ask ourselves. What assumptions have we made in making this interpretation of the strata? What assumptions have we made even in the observations that we've taken from the strata? And then there's the issue of non-uniqueness, which essentially means that the same pattern can occur for different reasons. So in this case, the low stand fan interpretation says it's an allogenic control, but what about autogenic processes? How might they be responsible for a succession of rocks like this? And then finally, I think the thing that we need to ask in our interpretations of strata like this is how much can occur by chance? Now, chance is a tricky concept, right? Because geological systems are not random in the way that a quantum mechanical system is random, but they are complicated enough that they may contain little or no pattern, and that's typically what we refer to as random. So how much of the apparent pattern is really statistically significant pattern that is unlikely to occur by chance and really does indicate some external allogenic forcing in its origin? That's what we're trying to understand, I think, when we look at an example like this. So how do we do that? I think we have to take a quantitative approach, and it has to be integrated. And integrated is a great buzzword, isn't it? Because everybody says it. You know, sequence stratigraphy is all about integration, for example. But let me be specific about what I mean. I think we need to do the outcrop description and interpretation. We have to do it with as few prior assumptions as we can manage. And then once we've got that, we need to apply some quantitative methods. If we're going to talk about order and pattern, those have to be quantifiably definable things. We have to be able to say that what we're seeing is unlikely to occur by chance, and we need statistical evidence to demonstrate that that's the case, right? So then when we've got that far, the next question is, so how did it form? What are the different mechanisms that this kind of pattern can form by? That's when we get into the issue of or the methods of experimental analog and numerical modeling, right? Because that is a great way to actually understand what the different ways might be, what different mechanisms might be responsible for generating a particular pattern that we can see. Okay, so this is the kind of workflow that I would advocate. And I'm going to show you an example of essentially following that kind of workflow to try and explain something like the outcrop example that I started with. So the talk outline, I'm going to talk a little bit about this model, Lobyte3D, how it's formulated, what parameters we put into it. I'm going to compare two different model runs from Lobyte3D, one with a signal and one without an external signal. We're going to look at two different ways to extract that signal then and analyze it. One is to do with bed thickness trends. The other one is to do with spectral analysis and a particular phenomenon that comes from that we've referred to as a signal bump, which I will explain. So to get started with Lobyte3D, it's a reduced complexity model. So wrote it with Isabella, who's a PhD student who's just finishing up now at Liverpool. She mostly was doing carbonate modeling, but she got turned to the siliciclastic dark side just a little bit to do this work. Reduced complexity model means pretty much exactly what it says. It's not a super complex model. It doesn't include all the details of you know, turbulent flow or highly sophisticated fluid dynamics. It's very, very, very simple. It's entirely deterministic also, but it is physics-based. So, you know, as with any model like this, you hope that it's representing simple physical processes, and therefore we can have some confidence in the way that it behaves. And what it does is it models sediment transport as a process from downslope flow to, in something like a channelized form to a more dispersive depositional flow that then comes together to form lobes. It can run models over geological time, which is one of the advantages about a reduced complexity model. If you've got all the fluid dynamics in there, they tend to be models that will run, say, a few flows and take a week to calculate it. But a reduced complexity model can do 1 million years, probably in a few minutes of computer time. So that's a big advantage to the lack of complexity. And we're going to explore a few different cases of constant supply, variable supply. And I mean, you could do pretty much any kind of input conditions to this that you can dream up, really. So how does it work? How's it formulated? Model runs each have multiple flow events. So any model run is usually 1 to 2,000 flow events to stack strata. The flow operates according to topographic gradient, and the flow velocity comes from the gradient, but also from flow thickness, right? So we are doing simple modeling of flow velocity to calculate when the sediment stays in suspension and when it begins to be deposited. So while flow velocity exceeds a specified threshold, that's one of the model parameters, sediment moves down slope. And when it hits a grid cell where the gradient is less than that threshold, it begins to deposit. So that's analogous to the transition from channelized flow and bypass to lobe deposition. So once it reaches that threshold, it starts to disperse. And this diagram here is showing that the red zigzag line is the downslope flow. That's the point when it hits the gradient where it begins to deposit. And this would be the flow dispersing out and dumping its sediment. And there's a few equations there that show the flow velocity and how the dispersion and deposition is calculated. If you're interested, all the details are in the paper from JSR from last year if you want to read more about it. Now, in terms of parameters, all the models that I'm going to show you, well, two actually today, run on a 200 by 200 cell grid. That's 20 kilometers by 20 kilometers. It's 1 million years of elapsed model time, 1,000 flows, so one flow per 1,000 years. Every flow comes in at the same point on the grid, so that's basically where the arrow is here. And we've got hemipelagic deposition rate as background sedimentation, that's 0.05 meters per 1,000 years. And in the model output, each of the flows is given, the flow deposits is given a different color, somewhere between red and yellow, so that you can distinguish them, right? So here's the sort of 3D view where you can see a series of overlapping flows stacked on top of each other. This is the down dip cross section in this orientation, and this is the cross, a long strike cross section across there, okay? So this talk is essentially going to be comparing these two different model runs. We're going to be looking at a constant supply case, which essentially has got no external signal, because the supply coming into it and all the other controls on the model are basically constant through time. Okay, and that's contrasted with a second model run where the sediment supply inputs, so the size of the flows that are coming into the model, varies through time following this kind of sinusoidal pattern, from a minimum to a maximum with a 25,000 year period. Okay, so we're really, a lot of the point of this is to compare what kind of strata is produced by these two examples. And to go back to the original outcrop, remember I said that those Nauchem basin turbidites had been interpreted as low stand deposits. So they would be an oscillating sediment supply driven by an oscillating sea level control, right? In contrast to a situation where there was no oscillation in sediment supply, which is the other model that we're running here. So the comparison of these two models will hopefully give us some insight into how indicative that particular pattern that we saw in the strata with the on-off sand is of an allogenic control. Is an allogenic control required to explain that kind of pattern? Okay, so I'm going to go through the two models now. Hopefully you will see these animations when I run them. And this is the same animation from each model, or the same interval of time from each model. What you can see is all the flows stacking. And if you were watching carefully there, you will have seen basically an avulsion event where the flows went from being deposited over here to being deposited over there, right? Now, the interesting thing is that happens in both models. So we can argue by that it must be an autogenic effect. It's not being something that's driven, it's not something that's being driven by the oscillating sediment supply, because it happens in this model with the constant sediment supply as well, right? So what we're seeing is, let me just run it again actually. What we're seeing is gradual drift of the location of the flows, right? So now they're over here. But then occasionally sudden much bigger jumps to over here. I think there's one coming in a second. There it goes. And those jumps are essentially all autogenic, okay? And they're producing clustering in the flows, which is analogous to lobes. So what does this look like in cross-section? I mean, you can see straight away the two models are very similar, different in detail, but similar in overall patterns. And when we look at them in cross-section down dip, so here's the 3D view again, and here's the dip direction cross-section. That's what these two are, one from the constant supply model, one from the oscillating supply model. And you can see they look, again, different in detail, but similar in overall statistical style, you might say, right? There's a series of packets of red, yellow flow deposits, sandy flow deposits, separated by these intervals of gray. And both model runs show a similar kind of pattern. Here you can see the deposition's been up here, and then it's jumped further down dip into the basin. That's in the oscillating supply model. In this one, there's been some backstepping, a jump up to here, a jump up to here. But basically, the strata looks surprisingly organized, actually, is what I always think. What about in strike sections? This is where I think it's really apparent. What we see in both models then is clustering of the flow deposits, right? So there's one cluster, what you might argue is a lobe, there's another cluster, and so on through the strike. And it gets more pronounced as the topography being produced by the model grows. So as we produce more topography on the base and floor, that has more and more control on the flow routing, and this construction of discrete lobe units becomes more and more pronounced. Right now, none of that is particularly surprising, except for this one thing, that this is a reduced complexity model. It's absolutely as simple as it's really possible to make a model like this and for it to still work. All it does is look at the topography of the flow of the basin floor beneath the flow and choose the steepest way down to the basin floor. And that's pretty much literally all it does. Yet from that very, very simple formulation, we get this clustering of flows and the production of lobes. And it doesn't look appreciably different between the constant supply model and the oscillating supply model. So that still kind of blows my mind a little bit, actually, even a couple of years after we first saw these results. I just think it's really cool, kind of arguably emergent behavior, in the sense that nobody explicitly tells the model to do that. It's an emergent property of simple rules that govern how the flows behave. Okay. And here's a nice example just to show, if there's anybody watching from industry or who uses seismic data a lot, we can generate really nice synthetic seismic of these different cross sections to see what they look like with different signal frequencies and so on. And that's something that we're investigating more now, because obviously it's interesting to see what stacked strata like this with various different offset sand bodies would look like in a seismic section. I'm sure you can see why that might be interesting. And then in terms of chronostratigraphic diagrams, so now we're looking at those same strike cross sections, but now plotted against time versus distance instead of elevation versus distance. And here again, you can see the separation of the lobe units really nicely. Okay, so you can see it on the cross sections, but you can see it on the chronostrat diagrams again. And you can see that that differs in detail between the constant supply case and the oscillating supply case, but it doesn't differ in overall form, if you like. The models are different in detail, but overall, in terms of their overall sort of pattern, they're very similar. Okay, so the autogenic lobes are occurring in both cases. They don't seem to have anything to do with allogenic forcing. And when we look at some vertical sections, so this is a constant sediment supply vertical section. It's about 48 meters of strata, similar for the oscillating supply case. You can see it's very much on, off, sand, mud, repeat, organized into these discrete lobes. And again, that's an emergent property of the behavior of the model. It's pretty much, it is purely autogenic. It occurs in both the constant supply and the oscillating supply case. And it looks to me, at least, and maybe I'm biased, but it looks to me very much like what we saw in that Nauchem basin turbidite example, discrete packages of sand separated by muddy intervals, but in this case, all an autogenic effect arising from flow over a simple evolving topography. Okay, so now you might say to yourself, that's ordered. There's a very strong pattern to those strata. Okay, but you know, if you start running random models, you'd be surprised what can emerge just by chance. So we need to be a bit more certain that the apparent pattern that we're seeing in these vertical successions really is indicative of some level of measurable statistical order in the strata. So to do that, we're going to do that in two different ways. And look at bed thickness trends first of all, and won't go into the statistical details, but it's pretty simple. Essentially what we do is we look at examples like this and calculate a metric which distinguishes between something that's clearly ordered with a thickening upward followed by a thinning upward trend like this one, versus something that's a bit more disordered or you know, likely to occur by chance. So here there's just a random stack of thicknesses. So in that case, for the ordered one, it's the R value that we calculate. This statistical metric is 2.5. For the disordered example, it's 1.25, right? And the difference between those numbers is essentially distinguishing between an ordered and a disordered case. And what we can then do is, for every example that we look at, we can take the particular vertical section that we've measured or that we've got from the model, shuffle it lots of times, repeat that process, calculate an R value for each one, and then we can work out a distribution, a statistical distribution of the R values that are likely to occur when the beds are randomly arranged. right? And that's what these blue lines are. It's a Monte Carlo method if you're interested in the statistics, and it generates a distribution of R values as a random model, right? But the really nice thing about that is we can then take what we actually observed in the model in this case, but also in outcrop, and compare it with that random model and say, are they different, or does the observed example fall within the random model or outside? So in the ordered case, this simple cartoon case that's, you know, visibly ordered, the observed value of 2.5 is well outside the Monte Carlo range of random values. But for the disordered case, thank goodness, the observed R value of 1.25 is pretty much slap bang in the middle of the random distribution. So this is a great test that allows us to make the distinction between something that's ordered and something for which there's no real evidence of order. So, you know, you could be considered to be disordered. All right. And the other nice thing about this plot is we can calculate from a p-value, so a probability basically. What's the probability of this observed value having occurred by chance? In this case, it's very low. In this case, it's quite a bit higher. So this one has got strong evidence for order. This one's got only very weak evidence for order. You can probably say it's random. Now, if we do that for all of the vertical sections in the model, that same basic calculation, we calculate that p-value. So remember, a really low p-value indicates order. That's color-coded as green. A much higher p-value indicates disorder. That's colored basically yellow to red. And you can see then how that begins to map out on the fan, which is very interesting, right? We find that there are some places on the fan, like round the fringe here, where the beds are very, very thin and there's a pretty complete record of what's going on. There, we tend to find evidence for order, but also in the mid-fan zone, actually. So around here, you can see those sort of streaks of ordered strata that are running down across this map view of the fan. So that's the fan outline from above, in case you're wondering, strike distance, dip distance. Previously, we were looking at cross sections that went through here and through here. Now we're looking at the plan view. And when you compare the constant sediment supply version with the oscillating sediment supply version, you can see there is a bit more order in the oscillating sediment supply case that we can pick out with this bed thickness analysis, but not much. Okay, this is still the autogenic constant supply version is still pretty ordered, and that's because the autogenic processes impart some order to the fan strata just intrinsically, even without the allogenic external controls. There's emergent order from the autogenic stacking, right? So for those of you who go out into and do outcrop interpretation, this is really important to consider, right? You can't simply say, even with statistical evidence, oh, it looks ordered and therefore it's allogenic. It's just more complicated than that. And I know many of you probably realize this, and that idea is actually gradually taking hold in the literature and everything. But still, you'd be surprised how many interpretations say ordered external control, disordered, well, you know, we're just going to ignore that. Or they never really consider when it's an ordered strata may equally well be autogenic. But I think this is showing that's pretty clearly the case. Okay, now the final thing. Spectral analysis, which is a bit more complicated, and I always used to avoid it because I think there are more than a handful of worms involved in this technique. But then Stefan persuaded me that it's really good, and yeah, well done, Stefan. I'm a convert, if that's a good thing. So spectral analysis simply takes looks for some periodic signal in the bed thicknesses in this case, right? And it can extract, in simple cases at least, that periodic signal very effectively. So in this really simple example, we've got two superimposed sinusoids which are causing the sediment supply to oscillate through time. It looks kind of complicated. It isn't really. It's just two sinusoids superimposed with different periodicities, right? And one 50,000 years, one 20,000 years. And you'll see that this is the kind of result we get from a spectral analysis of this signal. And it picks out two peaks that are exactly at the input signals that we put in. So no surprise, the spectral analysis will pick out from a simple case like this what the input signal was. Now, if we, but then what we have to do is something a little bit more complicated, because when you look at a spectral, a power spectra from an example, from a model or from an outcrop, what you see is lots of peaks. So looking at this one, there are several peaks in this series. Some are bigger than others. So what we need is some sort of measure of which could occur by chance and which are unlikely to occur by chance. And that's essentially what this green line tells us. If the peaks get above that green line, they're very unlikely to have occurred by chance. And this is using another one of those Monte Carlo techniques to actually set up a random model, which we then compare our observed power spectra with and say, okay, the peaks that stick above the green line, they're good. They're telling us that there's something that's ordered, indicative of a non-random process. And you can see the constant supply model has two peaks. One of the significant peaks is at 42,000 years, which nothing to do with Milankovitch, but 42, answer to life, universe and everything. I mean, it's a gift from a model when you get the answer 42, isn't it? I always think. So that's from the constant supply model. And then the oscillating supply model actually, interestingly, has several peaks sticking through above the green. And there are various reasons for this, but essentially what we're seeing in both cases is significant peaks. We're seeing significant periodicity in the model, both in the constant supply autogenic only example, also in the oscillating supply allogenic controlled model. So both have periodic content, okay? The interesting thing here is how would we really know which of these was allogenic and autogenic if this wasn't coming from a model? This is what this really highlights to me. Unless you know an awful lot about the system up front, if you got these two results from outcrops, you wouldn't necessarily be able to tell which was an allogenic effect only and which was an autogenic effect only. It's quite hard to tell, right? Unless you know from the sources. And again, we can do a similar thing about mapping where that order occurs on each fan. And you can see now, though, the distinction between the bits of order. Here we do start to see a difference between the constant supply model and the oscillating supply model. Those green dots are places where there's good order in the vertical succession from the spectral analysis. There are far fewer green dots in the constant sediment supply thing. So this is telling us that, with a few caveats, the spectral analysis will really start to tell us when a signal is present and when it's not. So, Stefan had a point. It's a powerful technique for that reason, okay? But we still wouldn't know for sure if we saw this example from mapped out from a fan in the ancient record from lots of outcrop sections. We still wouldn't really know for sure whether that was an autogenic or allogenic effect, because you do get periodic signals from the autogenic case. It's just a question of how much. Okay. Now, the other thing we can do then that helps us summarize these two maps into a single sort of metric for whether or not there's an external signal recorded in the strata or not is this final technique here. So if we take each vertical section on that map and we count the number of significant spectral peaks, we can plot the number of peaks against the frequency that they occur at, and we get these two plots. So one from the constant supply model, one from the oscillating supply model. So this is basically a count of all of the significant peaks from the spectral analysis that occur in this constant supply model. And you can see there's a lot of significant peaks at the low frequencies, and then it trails off, okay, like this, following a more or less sort of exponential trend. Okay, so that's basically the pattern that we see that is characteristic of the constant supply model. In the oscillating supply model, where the input signal was at about 25,000 years, I think, we see this bump, this jump in the number of significant peaks at and around the signal period. And this is what we were referring to as the signal bump, because this is telling us that in this case, there is some external, well, potentially some external signal that's driving production of these significant peaks coming out of the spectral analysis, all right? So a signal bump around the input signal frequency. Now, we've done this with a model. There's nothing to stop this being done with outcrop data. Okay, and it wouldn't absolutely prove allogenic control, but it would be indicative that, you know, that it probably is happening. Okay, so this is something that would be really, really cool to try. An outcrop example where we've got enough vertical sections, 20, 30, maybe more if possible, that we could try and put together a series of spectral analysis to create this kind of plot and see whether we can see any kind of signal bump or whether it looks more like this. Can we, you know, can we make the distinction of that outcrop example based on this technique? Okay, so then one final slide. The work that Rob and I have been doing since and arguing about a lot, and actually getting bogged down in some fairly complicated details of spectral analysis, which I blame all on you, Stefan, right? It's all your fault. We're trying to look now at running lots and lots of different Lobyte models with a range of different input signal periods and amplitudes. Okay, and that's basically what this diagram is showing you. Okay, so each of these squares is a model run which generates fan strata of the type that we've been showing, and then analyzes it to try and detect the presence or absence of this signal bump. Okay, and red basically means signal bump absent, green means signal bump present. Okay, now when you look at the input frequencies and amplitudes, it's kind of surprising because where we see the signal bump recorded seems to be high amplitude, high frequency signals, not the high amplitude, low frequency, longer period signals. There's no signal bump evidence. It's all down here at the high frequency, right? And one of the reasons Rob and I have been arguing so much is because that's not really quite what we expected. It's a little bit, you know, counter to what tends to get described in the literature. Also, it's quite difficult to explain, and we're trying to actually figure out what's causing that. The best explanation I think we have is that this is something to do with stratigraphic completeness, right? That simply for the longer period signals, they just get broken up. They're not preserved. I hesitate to say shredded because maybe it's something that should, a word that should be reserved for wheat, but they're not preserved for whatever reason, probably to do with stratigraphic completeness. Whereas the higher frequency, because they're shorter duration, it's easier to get a package of strata that records a significant chunk of that signal in one package. But when the stratigraphic completeness when you've got low stratigraphic completeness and the signal is a longer period, the chances of it being preserved are much less. So I think it's something to do with that, but we're trying to actually really prove that from the model results, and that's what's a little bit complicated to do. Okay, so I've completely lost track of time. There you go. So conclusions then. Lobyte3D, very, very simple model. It's a reduced complexity model, so there's very little complexity in it. But yet it does show emergent behavior. It shows clustering of deposition to form lobes. It shows lobe switching. It shows wonderful compensational stacking simply from the very simple physical laws to do with flow over an evolving seafloor topography. And ordered strata form due to that autogenic process, irrespective of an external signal or not. In one vertical section, or even a few, it's going to be difficult to distinguish an allocyclic from an autocyclic signal without knowing a priori what you're looking for. And you can't assume that it's a particular periodicity, something to do with the M word, because that just leads you in a logic circle. If you assume that and conclude that all in the same, I don't think you've done anything other than go around in a circle. So I would argue that even if you do see that evidence of order, it's difficult to tell whether it's going to be autocyclic or allocyclic, unless you can measure lots and lots of vertical sections and start to put them together into something that shows this signal bump effect. There, the evidence from this modeling says there is some distinction. The autogenic example does not show a signal bump. The allogenic example does. And we're using that now to try and, that distinction, to try and follow up and figure out when signals get preserved and when they don't. And as I said, Rob and I are still arguing about it a lot. Okay, I think I'm done. It's very strange talking to nobody, by the way.
You have 61 participants here, so it's not quite
Ah,
much.
no, well, I mean, that's great. It just feels like I'm just talking to my wallpaper behind my screen.
No, it's fantastic. Thank you so much for that talk, Pete. Um, Fantastic images and really interesting things to think about there, definitely. So whilst everybody is typing their questions into the chat, I just want to let you know that if you're watching this as a recording, please head over to the forums and you'll still be able to ask questions there when we have them back up and running, which will be soon. And we can continue this conversation for however long it needs to go on for. So I'll start with some of these questions then. So we have a question from Mauricio, suggesting to go to the Karoo Basin to look for signals.
Yeah, but I mean, I think the existing outcrop database is probably good enough that you wouldn't even really need to collect any new data. I suspect that if we just looked at the various logged sections that people already have, we could do it. Yeah, it'd be great. I'd love to do that.
Great. We have another question from John Raymer saying that asking, sorry, what would be the effect of catastrophic events in both models?
Well, yeah, it depends exactly what you mean by a catastrophic event. I mean, each event in Lobyte is something equivalent to a turbidity current, transport and deposition event. If by catastrophic you mean really big ones, I don't know, I guess you'd produce a great big pile of sediment on the basin floor somewhere, and then you would see a distinct reordering of the routing around that for the subsequent flows. Does that answer your question, John? Is that what you're asking?
If we ask John to post again, then we'll find out when we get to the list.
Okay. I'm gonna.
Yeah, he says yes.
Yeah, so I think that's what I think it would be flow rerouting. You would see, it would have a big impact on those lobe geometries, because basically you just reroute everything potentially after the catastrophic flow.
Great. Our next question is from Peng Fei Hu, who asks, regarding the signal bump histogram, if you lower the resolution of the measured sections, will the histograms look the same, particularly the low frequencies, long periodicities? They can only be seen in very long sections or high resolution, so how would it look in a periodicity domain?
So the periods that we were looking at there, the long periods that I showed in that matrix of red and green dots, that was still only about 100 beds. Right? So it was sediment supply oscillations on the scale of about 100 flow events. So you're right, but I think in a good outcrop example, like the Karoo or Naukem Basin, you'd have long enough sections that you would be able to see both the long and the short period events, enough that you would be able to resolve the signal bump. But if you only had very, very short sections with 10 beds, probably it's not going to work. No, you will probably need a longer record in each case than that, I think.
Great. Our next question is from Ajit Singh, asking, is there any possibility for input from field data, such for field-based estimates on sediment supply and that kind of thing?
Yeah, so I didn't really say, but we based the flow sizes in these model runs on sediment output measured from modern rivers, and I think we took the annual supply from a typical mid distribution from the whole size distribution of rivers across the globe. I think we took a mid-range value to get what we consider a representative sediment supply. So you could change that and you could make it fit whichever particular basin example you're interested in, either a really small Californian borderlands type fan, or maybe a really big one like the Mississippi or the Amazon. I mean, there are some modeling constraints, I think, on the really big flow volumes, because sometimes the model dumps everything in one spot, and you have kind of well, how to put it, I suppose, grid size issues maybe. There's some things like that you need to consider, but you can certainly change those sediment supply input parameters and make them reflect a particular example that you're interested in.
That's great. Next question's from Jacobus, who asks, well, it says, excellent talk, Pete, thank you. Natural allogenic signals will have a mixture of oscillation periods, such as Milankovitch cycles. How will this be reflected in the signal bump? Will it become less pronounced?
That's a good question. Yeah, a good question. I mean, that signal already kind of smeared, onto a better word. You know, if there's that 25,000 year signal that went in is getting chopped up by incomplete recording in the strata, and it's basically that spreads it out over the range of frequencies that you see across the width of the bump, right? So the more that happens, the more multiple signals you get, and the more incomplete the strata is, the more smeary it gets. And I think, you know, the really sort of hardcore Milankovitch interpreters say the signal's always there, just smeared out so that you can really see. But, you know, I would argue the problem becomes, if you can't see it, you shouldn't simply assume that it's there and you can't find it. You know, you need the actual evidence to show that it's there. And I think sometimes that can be lost in complicated cases, but then it's very difficult to tell whether it's just really complicated and smeared out or just not there to begin with.
Great, thank you. The next question is from Gary Hampson, who asks, what are the implications for how we should collect outcrop data sets, exposure permitting? How much data do we need, and from which part of the system?
Well, it's a good question. Those maps, and we've not really explored how indicative or realistic, if you like, this is, but both those maps of where the order seems to occur showed it was the mid-fan region that where it was best preserved. And again, it's one of those model things that I can't quite tell you exactly why that is, which is a bit embarrassing, because when you have a model, you should know everything about it, right? Otherwise, it's a bit of a Frankenstein. But I'm not entirely sure. But if you take at face value, it would be saying go to the mid-fan area and try and measure sections there, because according to those model output, that's where it occurs. I think probably before you went marching off to Karoo or wherever, and, you know, a month-long field campaign of logging at centimetre scale, I want to run a few more models to that specifically, you know, where the order is best developed. I've got all those models actually. I just haven't looked at the map, so I think that will be the first step. You know, run them with lots of different parameters and then see whether there's any coherent pattern to where you get most order preserved. And if there is that pattern, go and log there if you're looking for a signal. Does that answer your question?
We'll find out. So it's okay. We'll come back to that, Gary, if we need to.
Okay.
So next question is from Chris regarding preservation. He asks, is it erosion or just moving the deposition elsewhere that shreds the signal? Because maybe that explains the ordered bits in different parts of the fan.
Yeah, that's a good question, because yes, there's no erosion in this model, which is good news in one way, actually, because it makes it a bit simpler to deal with. So there's no erosion. So it is exactly as you just described. The reason that the signal gets shredded wheat is because things just get shifted around in the basin, not because anything's eroded, but simply because everything is incomplete. Right, so if you don't see a signal, it's because of incompleteness, not erosion. So that, and I think some people would argue, therefore, it's not actual shredding. I think I disagree, but I'm trying to formulate that argument a little bit more coherently before I say that too often.
Okay. The next question is from Noel Subi, who asks, thank you for an interesting discussion. I would like to ask about the frequency, the Fourier transform, and how I can use it to convert the age to age.
Well, I think that's tricky. I would, if you're saying how you can do it, I would say very, very carefully, and possibly you shouldn't. I think if you can keep the analysis to a bed by bed thickness analysis and make assumptions about the timing in it, then you should. In all the spectral analysis done here, there's no assumptions about time. I think what I do that maybe there's something hidden away in there, that's some hidden implicit assumption, but I've really been able to figure out it is. So I certainly wouldn't do what some Milankovitch analyses do and convert the section to time and then the analysis, because I think if you do that, you're almost certainly building in the answer before you do the analysis. And I suspect many cases that extract a signal have actually done that. So I think don't do a time conversion unless you absolutely have to. Just do the raw analysis and you'll get more reliable results.
Okay. The next question is from Yvonne Speichaler in Germany. And she says, regarding Karoo data, I have a big spreadsheet with data I used to do statistics on hybrid beds. Maybe that would be of interest to you, altogether over 25 logs and 23K beds.
Brilliant. I do love a big spreadsheet, Yvonne.
Maybe there's a future collaboration there.
No, that, I mean, it's a classic example, isn't it? And 25 logs, I think, is probably enough. If we did this analysis on all of them and put it together, I mean, whatever it produced, I think it would be interesting. Even if there was no bump, just a mess, it would still probably tell us interesting things.
The next question is from Yue Wang, saying, thank you for the excellent talk, Peter. I was wondering whether you could calculate the compensational timescale, such as in Strauss 2009, and will that timescale coincide with one of your unpredictable peaks due to autogenics? Secondly, in your high, or should we do the first part first?
Yeah, well, the answer to that is simple. Yes, I can. We have. I don't remember that it did correspond, however. And again, it's one of those things that Rob and I are discussing currently to try and work out what it means. But we certainly can calculate it and have calculated it, because you know it's a great statistic or metric to use, isn't it?
Great. Second part then, they've said, secondly, in your high amplitude short period scenarios, will one older cycle be completely eroded by a newer cycle at certain localities, for instance?
No, because there's no erosion in the model. So at any particular locality, bits of the signal will be missing because there was no deposition occurred there to record them, but nothing will actually be eroded. So that's what's interesting about this. I mean, I'm getting towards a view that you don't need erosion to shred stuff. You just need incompleteness if things go to different places. And then some people will, I think, you know, Carl Straub would argue, well, it's still all there if you look at sufficient volume. But then I even wonder about that now. I think there might be cases where, you know, practically speaking, you can't retrieve the signal, even if you've got access to that whole volume of strata, just because it's too broken up. So maybe there's something to be said for, you know, a theoretical shredding and a practical shredding. If you can't detect the signal by the methods that we have, then it's practically shredded, right? And I mean, that might be still distinct from theoretically shredded, that, you know, but practically it's going to be difficult to tell the difference.
Okay, that's interesting. Our next question is from Jinyu Zhang, saying, thank you for a great talk, Pete. This is Jinyu from Austin. Just wondering, in Lobyte3D, the evulsion is decided by random coefficient, or is it decided by slope or other parameters?
Just slope, Jinyu. There's no randomness in there. The only randomness, the only stochastic element in the model, I think, is when you get onto a completely flat base and floor and there's no gradient distinction between adjacent cells, and then it has to decide which one to go. And even then, I think it might just go into all adjacent at the same gradient from what I remember. But certainly the bulk of the behavior in the model has got no stochastic element. It's purely doing a steepest descent. And that's what's so amazing about it as an emergent property. It is deterministic, yet complicated.
Okay. The next question is from Pengfei Hu, who says, follow-up question, would you expect to see the same bumps in other submarine fans? Oh, sorry, it's just jumped.
Oh, that's a good question. I don't know. I mean, if you mean this, the signal bump, then personally, I wouldn't. I think I would expect most fans, if they have a controlling external signal, it's complex enough that it's going to probably have a different frequency in lots of different cases. But you know, I'm a little bit just that much skeptical about Milankovitch forcing. I think if you were following a Milankovitch model, you'd say that, you know, you should see the characteristic frequencies represented as signal bump, the same frequency signal bump in lots of fans globally. But, you know, that's something that we, with sufficient data at least, we could begin to test. And, you know, the Kourou outcrop example perhaps being the first one to look at.
That's interesting. So the other part of the question is different submarine fan environments. So between the channels and the levees and such like.
Yeah, well, I think the levees and the lobes are going to be more interesting places to do this kind of analysis than the channels. I think the channels are going to be too messy, right? Everybody loves a good channel fill, don't they? But from this point of view, for preserving a signal, you know, there's bypass, there's erosion, there's just going on there for it really to be a reliable place to look for the kind of signal bump that's coming out of this analysis. I would guess, but, you know, I mean, sometimes you can be surprised, can't you? So maybe there are channel cases that do preserve a signal, but that's not the first place I would look, I think.
Gary does say thank you. That's very thought-provoking. You answered his question well. That's fine. Okay, great. So that brings us to the end of our questions. Thank you so much, Pete, for answering them all, and thank you to all of you for asking such great questions. We hope to see you all at our webinar next week, which is going to be about glacial Mars and some morphological mysteries from another planet. So we're going to be taking a bit of a leap, and that's going to be presented by Francis Butcher from the University of Sheffield. And in the meantime, if you can't get enough of Seds Online, do come along to one of our coffee breaks and catch up with some of your fellow sedimentologists over this difficult time, as we're just all trying to find our feet again. So yeah, if you go on to sedsonline.com and you go and find the coffee breaks tab page, and then you can go and find out which zone you can go and come and meet people. So that would be great to see you all there. All right, so with that, I will close the meeting and say thanks again to Peter. Thank you to everyone here for coming. We've got some nice thank yous coming through for you, Pete. So thank you very much, and see you all next week.
Cool. Thank you. Thank you for the chance to speak. It was really good and great questions.